data set on gas mileage or fuel economy. So here we have the MPG of cars and we also have the weight. So I'm going to perform a linear regression of weight on miles per gallon, and the output is here below. And we see, you know, based on this model, that the model is given right here. And to form this model, we look at the coefficients column of this output. Um, but we also wonder, how well does this model perform? So we're going to discuss all of these metrics here, just on this right-hand side, starting with R squared and ending with BIC. Um, so one way to assess how well this model performs um, is to look at the regression, the graph of the regression against the data. And we can see, hey, look, it doesn't do bad on average, but there's usually cars that are both above and below that weight variable. Um, One way to try and account for this could be to add in extra input variables, such as the origin or the horsepower or the displacement, to see if that can account for why some of these data points are so far off the regression line. Okay, but on average it does a pretty fair job. One other thing about this model is that to go through the assessment of this model, um, we might, well, we not just we might, but it is a good idea to assess the assumptions. So does it meet the assumptions of the regression model? So if we look at the QQ plot, we see that there's a lot of points on this right-hand side that do not lie on the theoretical quantile line. Because of the quantity of points and the distance of the points from that theoretical red line, I would conclude that this data set does not meet normality. This is not due to random chance, that just a few points are lie so far from this QQ line. Um, but, and it's not just a few points. One thing to consider is how numerous it is. Okay. In terms of the other assumption of constant variance, we see the spread of these points is starting to increase as the fitted values increase. And that creates a classic horn shape. So my conclusion from this graph is that the data likely does not meet the assumption of constant variance. The data is likely independent because it's unlikely that one observation affects another's fuel economy. But one thing that we notice is, hey, there's quite a few points above and below. There's kind of a curvature to this line, to the data points. Instead of imposing a straight line, what if I imposed a line that had some curvature to it? Perhaps something like a 1 over x transform. So we can do that, and this is called a transformed model. This is the model that we're going to implement. Beta 0 plus beta 1 times 1 over x, where x is the weight variable. Okay? And if we do this regression, it looks like this. That's how the command works. And we get the estimates for the coefficients. So we see that the intercept is minus 0.5, so I missed that there. That's a minus sign. And that the coefficient for 1 over weight is 6.609 times 10 to the fourth. Notice that's a positive 10 to the fourth, so that's how I get that number there. We also see that 1 over the weight coefficient definitely affects the definitely affects miles per gallon, both from this p-value right here and from this confidence interval estimate. So its coefficient could be anything in this range. Okay, so the question is, how does this perform? And we'd like to use these metrics starting with r squared and ending at BIC to decide how well this model forms. But let's just review um, some of the model assessment that we already know. So if we look at a scatter plot, we could do a visual assessment. So instead of a straight line, here's a line with curvature. Does this fit the data a little bit better? It seems to be the case. Um, we could see if it helps to meet the assumption of normality, and we can see that there's still a lot of points that lie off this QQ line, so the conclusion would be that the data is still not normal. And in terms of constant variance, it looks a little bit better. Like it looks like the variance doesn't vary as much as the fitted values increases, but it still has this classic cone shape and seems to be increasing with the fitted values. So it, the conclusion for the variance would be it's likely non-constant variance, um, and the independence doesn't change. So I mentioned using some of the metrics. How can we use some of the metrics? Well, one of them is called the log likelihood, okay? And we saw that output right here. So the log likelihood is exactly what you think it is. It's the maximum likelihood, but then you take the natural logarithm, okay? So keep in mind, why can we use the log of the maximum likelihood? Well, our regression function looks like this, where this is a function of our input variables. We could have one or multiple input variables. In the model we're considering is just 1 over x, or 1 over x1, with one input variable. Then there's some random error that comes from a normal distribution with mean 0 and variance sigma squared. Because of this model, we can conclude that y is normally distributed with the mean of being the function, the regression function, and variance sigma squared. So our likelihood function looks like this. When we take the log of the likelihood, because this is always a number between 0 and 1, it's a product of probabilities, 1 indicating a good fit, a 0 indicating a poor fit. When we take the natural logarithm, those numbers range from minus infinity to 0. So, negative infinity for the log likelihood indicates a poor fit, 0 indicates a good fit. So now we can compare those two metrics, minus 1138, and here we have minus 1148. So this one's slightly more negative, not by a whole lot, but if we were to go off of that metric, the model I would choose is the one with the curvature. Okay. Okay, so that's one metric. Now, there's another one called AIC and BIC. And AIC and BIC are forms of the log likelihood. So here AIC formula is minus twice the log, is minus twice the natural logarithm of the likelihood function. So both AIC and BIC have that component. Now what this minus 2 does is it changes the interval of the likelihood function being from 0 to 1, it changes it to being from 0 to positive infinity because it's multiplied by negative 2. Okay? And the 2 is there for classic reasons to make formulas simpler. So the scale for both AIC and BIC is 0 to infinity, 0 indicating a good fit, infinity indicating a poorer fit. Okay, so we're looking for numbers that are closer to 0. And what this does is it inflates the error. So the AIC is inflated by 2k. Here, k is the number of input variables. BIC has a harsher penalty. This is inflated by k times the natural logarithm of n. So n being the size of your data. So the more data you have and the more inputs you have, the harsher the penalty for BIC. Okay. So we can now use AIC and BIC to assess these models. Okay. So AIC is 2281, 2289. Okay, this is 2309, 2301. This is larger, indicating a worse fit according to the AIC and BIC. Okay. Now, there's something called the F statistic. Um, the F statistic is calculated like this. So it's the log of the likelihood of the model with more parameters minus the log of the likelihood of the reduced model, the model with fewer parameters. Okay. K1, that's the number of parameters in the full model. K0 is the number of parameters in the reduced model. Okay. Um, there's an equivalent formulation to this F statistic. It can be calculated by this or like this. They're the same thing. Okay. So here, this TSS is just the variability in the y. It's the observation minus the average. The RSS is going to be the observed value minus the predicted value. Okay. Um, then there's an important thing to consider here is that this can be used for hypothesis testing. You can use the F statistic. The F statistic here has a null hypothesis that your reduced model is adequate against the alternative that the full model is better. Okay, so we can use this F statistic, okay? Um, so by the way, the smaller the F statistic, the better. So here, the F statistic is 954. And here, the reduced model is just the model that predicts the average. So this F statistic says that having the input of weight is way better than having a null model of just predicting a constant miles per gallon. The constant would happen to be the average, and we'd reject that we should use the average as the predictor. With this p-value, it's very teeny. It's 1 times 10 to the minus 107. It's very, very small. Okay. Okay, so that's 954 versus 888.9. So this F statistic gives some indicator that just the simple model with the line is better here because it's a smaller F statistic. This also indicates using the predictor, but now the predictor isn't transformed, is better than predicting the average with this p-value. Okay. Okay. Now there's something called adjusted R squared. R squared is calculated like this, and the adjusted is calculated like this. They both have the same meaning here. And how you would interpret it is that either one, whether it's adjusted or non-adjusted, it represents the proportion of variance that the model explains in the data. And it ranges from 0, explaining 0% of the data variability, to 100%. Okay. By the way, you only typically adjust if you have more than one predictor. So if you use multivariate regression. Okay. Okay. Um, so let's look at those metrics. So for the transformed model, the R squared is 70.7 versus 0.706, so they're basically the same. Whereas the non-transformed is 0.69. So these are basically the same value whether you transform or not. I'll say this. If you're strictly going off of the metric, the one that explains a little bit more of the data is the transformed model with 70% of the variability, 70.7. But is that due to random chance? Possibly, because the difference is so small. So to me, the difference in R squared in the two models is negligible, and it's an indicator that you could use either model. Statisticians typically prefer simpler models. So typically we would take this simple linear regression one if we were going by R squared. If we were going by AIC or BIC, we would go with the transform model. So your conclusion is linked to what metric you use. Okay. And just one more thing, the p-values of both of these tells you that the input of weight does affect the output of miles per gallon. Okay. Okay. Thank you very much.